There are a few more variations we're going to talk about right now. They're kind of in the family of variable step size. The first of these is the MomentumLMS algorithm. This algorithm looks just like what we've seen before, but we're going to add in an extra term. And this extra term is reminiscent of what we did with our variable step size, where we increased mu when we had the same sign in the error in multiple runs, versus when decreasing it when the sign began alternating. But in this case, instead of actually having some sort of decision being made, we're just going to pick a single alpha. And this alpha is multiplied by the weight difference last time. So this has the effect of, if we start moving in the same direction and we have a positive alpha, then we'll keep moving in that direction faster and faster. So as this difference increases right here, then the total update will then increase, and the difference between these two values will be larger, and at the next value of n, the difference in those now becomes the difference in these, which is now larger. And you can see that we will increase faster and faster until we finally start to get corrections in the other direction, which will slow things back down. So in order for this to work, surprisingly, mu can actually be a little bit larger for positive alpha, and it turns out it works for negative alpha, but I should put works in quotes because it will converge, but the performance is worse. So we generally want alpha to be greater than 0. It will converge in the mean under these circumstances. However, the misadjustment error is going to be a little bit larger. And so if we decrease mu by a factor of 1 over alpha, sorry, 1 over 1 plus alpha, reduces misadjustment error. Of course, it always would reduce it, but approximately back to LMS levels. So in this way, we can actually pick a relatively small value of mu so that we get good performance with our misadjustment. And this is how it would best be used. Pick a small value of mu, and in the early steps we'll have our early stages of our adaptation, we will have effectively larger and larger steps, and then as we get closer, the steps get small again. Okay, so the MomentumLMS in some ways appears to be one of the very effective ways of dealing with this desire to have a fast adaptation when we're far out and a small adaptation when we're close, and very few parameters in this case to choose between as we figure out how to run this particular setup. Okay, we're going to switch gears just slightly because I didn't want to have a 4-minute lecture and then another 4-minute lecture, and this is yet another variation on the LMS algorithm, but the idea is different for the p-vector algorithm. For the p-vector algorithm, we are not doing as we've done in the nearly every variation so far. and looking at ways of either making it converge better or faster at first and finer near the end, or be computation more efficient, such as the sign algorithms. The p-vector algorithm actually works if we don't have a desired signal. Well, everything we've done so far requires us to have an error and a desired signal. So you can imagine this doesn't work quite as well. But effectively what we're going to do, we still have to have some idea of the target that we're shooting for. So we're going to replace dn xn with the expected value rdx. So I guess we do need to have that. So let's look at how this would play out. Suppose we had that x of n was equal to d of n plus some noise that was uncorrelated with d. If we happen to know the autocorrelation of d, then we can find the autocorrelation of dx in this case. We can use this to form a vector, rdx is now just containing rd0, rd1, and so on. So now we have a weight update that looks like this, where this last value rdx is formed from our autocorrelation of d. Okay, this is the algorithm in general, but in this particular case we have this relationship that we know from d. There may be other cases where we happen to know something about rdx, but we don't have a particular desired signal at any particular point in time.